Welcome to Daily Papers, where we break down the most interesting new research. So let's talk about AI. We ask large language models, or LLMs, all sorts of things, right? What's the capital of England? Write a poem about my dog. And they're amazing at it. But here's a bigger question. Do these AIs actually understand the world, or are they just incredibly good at memorizing facts from the internet?
That is the multi-trillion-dollar question, isn't it? And it's exactly what a new paper called Epidemiology of Large Language Models tries to figure out. The authors make a really important distinction between two types of knowledge. First, there's factual knowledge. That's the capital of England type of question. It has one correct, verifiable answer.
Right, that's trivia. AI is great at trivia.
Exactly. But then there's a second, much deeper type, probabilistic knowledge. This is about understanding the statistical patterns of the real world. A question here wouldn't be, what is the capital of England, but something like, what is the gender distribution of computer science graduates in the US? There isn't a single true or false answer, but a probability. It reflects the messy, uncertain reality of the world.
Okay, so factual knowledge is knowing a specific fact, while probabilistic knowledge is knowing the odds and tendencies of how things are in the world. So how on earth do you test if an AI has this kind of knowledge?
Well, that's where the epidemiology part of the title comes in. It's a brilliant metaphor. They decided to study the knowledge of what falls upon populations within these AI models. They built a massive test, a benchmark, using data from 10 huge real-world US datasets. We're talking the US Census, the Centers for Disease Control, the Department of Labor, all of it.
So they have the ground truth about how society is structured, statistically speaking.
Precisely. Then they asked a bunch of different LLMs questions based on this data. For instance, they might ask, what is the race of a person working as a librarian? Or what is the sex of someone who graduated with a degree in physical sciences? They then compared the AI's probabilistic answer to the actual statistics from the real world.
That's a clever way to do it, but why is this specific kind of knowledge so important? Who cares if an AI knows the demographic breakdown of librarians?
Because this is the absolute bedrock for any kind of sophisticated reasoning, especially causal reasoning. The authors frame this using a concept called Pearl's causal hierarchy, which is sometimes called the ladder of causation.
A ladder of causation. Okay, that sounds cool. Break it down for me.
Imagine a three-rung ladder. The first and most basic rung is observation, or seeing. This is exactly the kind of knowledge we've been talking about, understanding the world as it is. It's about seeing correlations in data, like noticing that people who smoke are more likely to get cancer.
Okay, that's layer one. What's the next rung up?
Rung 2 is intervention, or doing. This is about predicting what will happen if you actively change something. It's not just seeing that smokers get cancer, it's asking, if we make a law that forces people to stop smoking, how will cancer rates change? You're intervening in the system.
And the top rung?
That's counterfactuals, or imagining. This is the what-if rung. For a specific person who smoked for 20 years and got cancer, we ask, what if they had never smoked? Would they have still gotten cancer? It's about imagining a different reality.
Seeing, doing, and imagining. I like that. So where does this new paper fit in?
This is the crucial part. The causal hierarchy theorem states that you cannot reliably climb to a higher rung on the ladder without a solid footing on the one below it. You can't reason about interventions or counterfactuals if you don't first have an accurate understanding of the world through observation. And this paper is testing that very first rung. They're checking if LLMs even have a grip on layer 1, on seeing.
So if they fail at this basic level, there's no way they can reliably do cause and effect reasoning, which is what we'd need for AI to really help in science or medicine or policymaking.
You've got it. And the researchers made the test even more challenging by looking at something called the curse of dimensionality.
That sounds ominous.
It is for statisticians. It just means it's one thing to ask about the probability of having diabetes. It's another, much harder thing to ask about the probability of having diabetes given a person's age, race, sex, and income level. As you add more conditions or dimensions, understanding the relationship becomes exponentially harder. The researchers tested the LLMs on both simple, low-dimensional questions and these much trickier, high-dimensional ones.
Okay, so the moment of truth. They've built this incredibly rigorous test for the most fundamental level of causal reasoning. How did the AIs do?
They performed very, very poorly.
Really? I would have thought they'd soak all this up from their training data.
You'd think so, but the results are pretty stark. They created a scoring system where 100 is a perfect score, meaning the AI's understanding of the world's probabilities matches reality, and 0 is no better than random guessing. The best performing LLM scored around 22 out of 100 in the simple setting, and only 17 out of 100 in the harder high-dimensional setting.
Wow, so they're better than a coin flip, but not by much. What does this mean for the future of AI?
It's a huge reality check. We hear a lot of hype, with some people claiming that LLMs are becoming universal approximators of distributions, basically that they can learn the statistical patterns of anything. This paper provides hard evidence that no, they are not there yet, not even close.
So when we ask an AI to weigh in on complex societal issues or to help a doctor with a diagnosis, we should be really careful because its underlying statistical model of the world might be very shaky.
That's the key takeaway. It's not that these models are useless, but their knowledge seems to be more like a vast but shallow ocean of facts, rather than a deep, structured understanding of how the world actually works. For AI to move from being a fancy search engine to a real partner in scientific discovery, it needs to get a grip on that first rung of the ladder.
It seems knowing the facts is one thing, but understanding reality is another entirely. This paper has built the benchmark to prove it.
Exactly. It gives researchers a clear target. Don't just make the models better at trivia, make them better statisticians. Make them actually understand the world they're reading about.